Your early experience was with in the early days of the Apollo program, I gather, looking at how the moon could be used. Tell us a bit about that.
Okay, yeah, I did my PhD in space physics and astronomy at Rice University back in the 1960s, and after graduation I worked for TRW Systems down here in Houston during the peak of Apollo. Immediately after that, I joined a group set up by the National Academy of Sciences called the Lunar Science Institute. And so I was there all of the 1970s, and from the administrative standpoint, the thing that I started out on was managing the review of all the proposals submitted to NASA for lunar science and the solid planets. And that involved over 7 years about 3,500 proposals. So I was deeply involved in that, in managing the review.
When did you begin to see that the moon was a possible source of solar energy for the planet?
Well, that took a while. During the mid-'70s, NASA and DOE expended about $25 million on studying how you would put satellites up from Earth to capture solar energy in space and then bring it down to Earth in the form of microwaves. And that was a fairly large study. It involved several major contractors, virtually every NASA center, and also the Department of Energy. The end result of that was by 79 or 80, it was realized that it would be far too expensive to provide commercial power back to Earth. Around 76 or 77, I received a grant from NASA Langley on how you would take common lunar material and use it for engineering purposes, how you'd build stuff with it, how you'd process it in such ways that you could build useful products. And you can build almost everything in our modern economy out of the lunar soil, either the bulk lunar soil or stuff that you would extract from it, beneficiate from it is the technical term, or mine it. And I was working with Dr. Bob Waldron, and we were discussing the moon, and then we sort of looked at each other and said, well, why bother building a satellite in space? Why bother building them on Earth and sending the parts up and putting them together? The moon exists. It's far, far larger than anything that we could build. And we knew by that time that you had all of the resources you need to not only build power stations on the moon, but also, in some ways more importantly, build most of the tools that you would use to build the satellite, to build the solar receivers and transmitters on the moon. And so that's the kernel of the idea. We had the knowledge of the Space Solar Satellite program, and we could leverage that $25 million worth of engineering and environmental research. And then in addition, we knew from this research grant, which was about 5 person years over its entire life, that the common materials, which were well understood by the mid to late 70s, were completely adequate to provide all the materials you needed to work with. And that's the key to the reason that lunar power can be commercially successful. Rather than sending up all of the parts via our onboard expensive rockets, you send up the small factories which put out hundreds to thousands or even hundreds of thousands of times more product in mass than the mass of what you send up. So that brings the cost of the transportation down very, very low. And in the late 80s, when I took all of this and information and put it together into an engineering spreadsheet based on later NASA-funded studies, I was immediately realized that this would be at least 50 times less expensive than sending satellites up from Earth. And immediately it brought down the cost of the energy delivered to Earth into the commercial range.
So the idea is you send up the capacity to produce factories
Yes.
not even factories, but the capacity to produce factories on the moon from lunar materials, and you build solar cells there, and you also build microwave generators that can beam the power back to the Earth. Is that correct?
Yes, the model that we used was essentially the magnetron in a home microwave oven. You're not restricted to that, but that's something that we clearly found that you could build out of the common lunar materials, out of the iron or aluminum, and the soils that make up the lunar soil are very good glass-making material. So you can build all of those active components. You can build reflective screens that can be segmented, but you arrange them over the moon in such a way, over portions of the moon, that to our eyes from Earth they look like a filled reflector array, a lens in effect, that allows you then to focus energy or power back on Earth very efficiently. And to give you a little bit of a feel for that, in the solar power satellite studies, we looked at, or the research groups found that a satellite which would deliver about 10 gigawatts to Earth, that's about what it takes to run the greater Houston area, would weigh about 160,000 tons when you put in all of the mass of the satellite and the maintenance mass and everything. That's also about the same mass that a set of antennas on the moon made out of the lunar materials would weigh, but those antennas could be 100 kilometers across. And rather than being restricted to 10 gigawatts of power, they could send back, accommodate the transmission of something like 2,000 gigawatts of power, 2 terawatts. So that's an example of how you can leverage the lunar materials to have far higher capacity, trying to send stuff up from Earth.
How does 2 terawatts compare with the consumption of electricity on the planet at the moment?
The Earth now produces about 2.5 terawatts of commercial power. Right now, we need about 16 terawatts to accommodate, or 14 terawatts at least, to accommodate 7 billion people. And in the middle of this century, we'll say 2050, there'll be about 10 billion people on Earth. You need at least 2 kilowatts electric per person, so you really need 20,000 gigawatts or 20 terawatts. And if you tried to produce that by burning, say, oil, you'd have to burn 1,000 million barrels of oil a day to produce that much electric power. Today, the entire world oil industry only puts out about 85 million barrels of oil a day. And I think we can be absolutely assured that world oil output will never approach 1,000 million barrels a day. In doing that, and putting out that much oil, the oil industry worldwide expends about $600 billion a year just to maintain that flow of oil.
That's not the cost of the oil. That's just the cost of keeping the whole process moving, shipping it from one place to the other.
Well, it's exploration and production. It's the cost to explore for the new oil and to put in the facilities to output it. There are a lot of other additional expenses, your pipelines, your tankers, your refining capacity, and all of that. The world spends about 15% of its gross world product, 10 to 15% of its gross world product, just to maintain its fossil energy systems and the fuel that powers them. If you were to take that $600 billion a year that's now spent just to maintain the 85 million barrels a day of oil output and invest it over 15 years in establishing the lunar solar power system, then you would start getting back a net profit about 15 years into that process, and thereafter the system would grow very quickly up to this 20 terawatt level and provide enough electric energy to have a prosperous Earth.
You cited the figure of 2 kilowatts per person. What do rich countries now consume in terms of electrical power, and what do poor countries like, Haiti or some other African countries or poorer Latin American countries?
Well, 2 kilowatts a person of electric power is about what is used in Western Europe now and in Japan. It doesn't hurt to have more. The U.S. uses the equivalent of about 4.5 kilowatts electric per person. You could easily provide that much electric power to Earth from the moon. Again, for 10 billion people, that would translates into 20 terawatts. And back on Earth, you would receive that power in large fields of radio antennas, essentially, called rectifying antennas or rectennas. And to receive that much power at 20% of the density of sunlight, about 210 or 230 watts per square meter, you'd need 100,000 square kilometers of area split into many different rectennas, receiving plots. It sounds like a lot, but it actually is very efficient compared to how we do energy and power delivery now. It would be about 5% of the land area that is used in the U.S. to deliver power.
5% of the existing land area in the U.S.?
No, the land area that's used in our present oil, natural gas, coal.
I mean the factories, the mines, the area covered by the...
Yeah.
The tar sands, for instance.
Well, tar sands are even more area intensive. This was a number that DOE came up with in the 1970s when they were comparing providing electricity, replacing the U.S. conventional electric power system with rectennas. The rectennas would only occupy 5% of the land area the U.S. used in the 1970s to provide the same power flow, about 300 gigawatts.
And what do these rectennas look like? What are they?
Well, to a first approximation, they might look like rays of solar cells, except they could be essentially transparent, because they could, instead of a solid sheet, they could be in the form of open grids of wires, diodes, and little antenna elements. And one of the things that means is that you could use the land underneath the rectenna. The microwaves would come in, be absorbed, at least 95% of the incoming beam be absorbed and changed into electricity. You could work under these rectennas completely safely. But you could also grow crops, or you could put these over shallow bays like the upper part of Galveston Bay, and still have it as a fishery. You could also put it over industrial complexes, or just you have options with it.
So at 1/5 the intensity of sunlight, is there any danger from the microwave beam?
No, you could walk into it. Animals could go into it. There'd be no danger. It will be, though, commercially, industrially zoned area, so you'd put a big fence around it, sort of like what you put around driving ranges for practicing golf, and exclude all but industrial workers from it. You could exclude virtually all larger life forms, beyond insects, and should be a very, very benign operation.
And a plane flying through it?
A metal plane could fly through it with no problem at all. You know where the rectennas are, though, so if you need to route planes around them, you could. 15
years, you're saying, at an expense of $600 billion, over 15 years, you can put enough of these sort of proto-factories, the ability to produce factories on the moon that will produce the solar cells and the microwave generators and the reflectors to send the microwave beams to the Earth, to produce, at the end of that time, how much power?
Well, that would be about enough to power the U.S., and that would be your break-even point. When you get to that point, you're selling the power at 10 cents a kilowatt electric hour. You could sell enough to pay all of the past investment. You could pay back the 500 billion to 600 billion back. You'd be then making money, and all of your future operations would be paid for out of the selling power to retail and industrial customers. As you go past that break-even point, the amount of power you're generating is going up exponentially. And so it's really up to how fast you want to grow. In another 20 years, you could be providing everybody on Earth with their at least 2 kilowatts electric per person. And you could also be bringing down the cost of that, the electricity that you sell. It should, over the life of the project, fall down to about a cent a kilowatt electric hour, so that everybody on Earth could afford it. There's we've got about 7 billion people on Earth right now. The great majority of those people, or half of the electricity is used by the developed nations. So they're using about 1 or 1.5 terawatts now of all electric power. The other 6 billion people either have very little access to electricity, or there are about 1 billion to 1.5 billion that have no access at all. There are parts of Southeast Asia and Africa that are like that. And their economic development is extremely restricted due to the lack of electricity.
Once it gets up and running, you could build a rectenna in any one of these regions and send a beam from the energy collected on the moon back to that rectenna and provide serious levels of electrical power to these countries at a cost that would maybe start out at 10 cents a kilowatt hour, but as you're saying, would go down to perhaps a penny a kilowatt hour.
Yeah, that's right. I mean, you need about 100,000 square kilometers of total rectenna area, but that's split into thousands of individual rectennas. The individual rectenna probably needs to be on the order of half a kilometer to a kilometer across. It can always be bigger, but with these large microwave lenses on the moon, you can focus power down to somewhat less than a half a kilometer across, maybe a couple of hundred meters. And you would start small in a given area and just start expanding the rectenna. And the thing is that once you got in your core rectenna, the expansion of it, again, it'll be putting out electricity. And as you expand it, it just puts out more and more electricity. And this would be load-following electricity with a mature system that you would, say you're powering Houston, maximum power would be coming in the late afternoon in the summer to run all the air conditioners. But at night, the power that you, say at 3 a.m. in the morning, the power you had been giving to Houston, you could transfer over to Australia or Singapore, anywhere else in the world that needs it. So it would be a very efficient system from the way it can deliver power.
So how would you get power to the Houston at night when it's not, assuming that the moon's not in the night sky?
The stations on the moon can feed power to receivers on Earth as long as the moon is 25 or 30 degrees above the horizon. So that's about a third of the time. That's also about the amount of time solar cells can get power directly from the sun if there's no clouds. But when you want to provide in the mature system continuous power into Houston, you would have relay satellites in orbit around Earth that would be high enough above the Earth that they could accept power from the moon all of the time, and they would redirect, reflect, or retransmit the power from the moon down to the receiver, the rectenna on Earth the rest of the time.
Would these relay satellites be an expensive part of the whole system?
No, because they can be relatively small, and electronically and mechanically relatively inexpensive. So they would not be a major cost item. And this is based on, again, the studies that were done back in the 70s of the solar power satellite systems. In that case, you had to have very large solar arrays to collect the sunlight and feed the sunlight into your microwave transmitter, which then fed it into into your microwave producing elements, which then were put together as a transmitting antenna about 1 kilometer across. That transmitting antenna was on the order of 30,000 tons in mass, because you had to have the clysotrons in that case to go from electricity to microwave. A redirector in the form of a mirror-like reflector would be a very thin sheet. It'd have to be high precision and controlled continuously to reflect down to the right place on Earth. There's a technology called reflector rays, which has evolved since the 70s, in which an incoming microwave beam impacts a thin film circuit that immediately produces an outgoing microwave beam. And those, again, would be as thin as a sheet of paper. And they have the potential of being up to 98% efficient in converting microwave to microwave. So these redirectors can, in principle, be very thin and very low mass.
So in the long run then, when the system's all set up, you have this energy being collected on the moon where there's plenty of sunlight. It always, at least if the moon is where the collectors are facing the sun, there are no clouds, it's regular, you know exactly what you're getting. And that's going to be beamed back to this array of satellites, which will then be able to send beams wherever they're needed and follow the loads and can deliver energy essentially anywhere on the planet.
Well, that's right. That's the mature system, and it would be like in the passive in the sense that a hydroelectric dam is passive. The water goes through it, but the dam turbines just spin. It all is just a smooth process that very efficiently taps our largest power plant, of course, which is the sun. Going back just a little bit, that's the mature system. This lunar solar power even makes sense if you build your transmitters on the two edges of the moon as seen from the Earth and transmit from one or the other to receivers only when they can see the moon. You would then have to have power storage or longer transmission lines on Earth, but it would still be far less expensive than trying to do the same thing with solar arrays on the Earth.
Say more about that. I mean, because it seems like having to go to the moon to collect the sunlight seems like a big expense and difficult, whereas collecting it here on the planet, we can of course do that already. We see solar arrays on people's houses already. Why is that not the way to go? Well,
the problem with solar on the Earth is you never know when sunlight's going to be interrupted. There's no engineering way to accommodate clouds and rain and all of this. So if you're trying to power the world's cities with solar, you're going to have solar arrays, huge solar arrays all around the Earth with big power transmission lines, at least in the technology that's normally been talked about. And you never know when several of those are going to drop out because of bad weather conditions, which could be due to weather. It could also be due to volcanoes going off, and you can think of the real scenarios. And when you model a global system like that, it turns out you'd be very lucky when you include power storage and transmission, to get more than 2 or 3 watts per square meter of power averaged over all of these arrays. On the other hand, if you're bringing in microwaves, which are engineered to go through the atmosphere, you can easily get out 200 watts per square meter, a factor of 100 to a factor of 50 more power per unit time. So when people talk about terrestrial solar on Earth, they always talk about right now. They don't talk about the real system that it would take to provide the levels of power that humankind really needs, which is at least 2, maybe 4 kilowatts electric per person. If you stand back and look at all of the options that get money now from government and private research, they never scale these systems up to what the world really needs.
So they're essentially schemes for producing power for the United States, but for the rest of the world, it's assumed that they're going to stay in the same level of impoverishment that they are now.
Well, that's right. You really need to have as your target a system that delivers a cent a kilowatt electric hour or less cost, and you need that because of the 5.5 billion people on Earth now who are essentially poor. And electric power is the absolute requirement for generating wealth. That's why China has as one of its highest national priorities is building more electric power plants, which turn out to be coal. They're trying to introduce electricity into their economy, and their growth is directly proportional to how much electricity they bring in. But they're limited. China of 1.3 billion people needs 2.6 terawatts or 2,600 gigawatts of electric power right now. They only have a fraction of that. I don't remember the number right now, but it's probably like 300 gigawatts. If they had lunar power rather than having to go all around the world looking for oil and natural gas and huge imports of coal, they just install the rectennas and they have all the power they need, not simply to run industry, but to recycle water, provide their residential needs, support their transportation. You wouldn't have to have this almost warlike industrialization activity to support their goal of having a prosperous China. And that's true around the world.
To conclude, would you share with us then the overall sense of your vision of what we could do by beaming solar power collected on the moon back to the Earth?
This is when you achieve this 20 terawatt or somewhat larger level, you would then have a world that is about 10 times richer than it is now. The average gross product per person would go up from about $8,000 a year per person up to over $80,000 a year. Your industry and all of this economic progress would be completely sustainable. There'd be no waste products introduced into the environment. If you and you can just keep doing that, and you'll get richer every year just because you learn how to use electricity more efficiently. It includes your baseline and industrial and civil activities so that you can maintain the environment in a completely clean state, and you can actually use the power to clean up the planet. If you expanded beyond about 30% beyond 20 terawatts up to 25 terawatts, something like that, you could use that excess energy, clean energy, to extract CO2 from the atmosphere and essentially remove all of the CO2 that has been introduced by industry since the start of the Industrial Revolution 200 years ago. So we would finally have control over our environment in two different ways. One, we wouldn't keep messing it up, and second, we could actually nurture it back to health. The other thing you would have is the moon would become an integral part of the world economy. By 2050, 2070, the gross product produced on the moon would exceed that of the United States. Now, it's hard to imagine what all would be going on, but there'd be an awful lot of science-based activity, but there'd also be an expansion of humankind out into the solar system. We'd no longer be living in a box. We could live beyond the box in habitats that we create. These habitats would be the endpoint of the development of cities as completely self-sustained human populations that simply need an energy input to keep going. So it would be the real independence of the human race from the constraints of growing up inside of our biosphere and consuming our biosphere to keep old engineering practices going.